Okay, good evening. So this is our lecture number 39, and in this we will continue our discussion on the volume of fluid method. Majorly we will be today in the concluding mode. So already I explained to you that in case of volume of fluid we treat our two phases using the one fluid formulation, and at the interface we introduce a surface tension force. Okay, and in addition we solve one more equation for volume fraction in order to determine the or differentiate the two fluids from each other. Here we have two steps. In one case, depending upon the value of the volume fraction, we construct the interface. So we have discussed already about the interface reconstruction techniques, and then in next step, because we have to also show the temporal evolution of the interface, for that what we do advection of the volume fraction field. So for advection of the volume fraction field, I introduced you to the scheme for one dimensional case. For two dimensional or three dimensional cases, I am not explaining that point. So any of you are, if interested, you can read the textbook direct numerical simulations of multi-phase flow. Okay. Then next point, if you see, already I told you that when we will be doing the volume of fluid method in a computational way, then we have to discretize our governing equations. So our governing equations are nothing but continuity, momentum and volume fraction equation. So discretization of volume fraction equation I have already shown to you, and regarding the discretization of continuity and momentum equations, particularly for Newtonian fluid, which are called as Navier-Stokes equations, I have given you the reference of 5 lectures of CFD from where actually you can learn that. But one important point is the lectures which I have already referred to you, these lectures will be showing the discretization of all the terms in momentum equation except for the surface tension term. So that's why discretization of surface tension term I have briefly included in this particular lecture. Okay. So using this brief summary, you can see that as a whole, if we look into the volume of fluid approach, so what we are doing for a steady incompressible flow, sorry, not steady, for incompressible flow, we are solving this as nothing but our global continuity equation. Okay, so we are not solving the individual phase continuity equations. Individual phase continuity equations only we will be solving when we have phase change heat transfer involved. If phases are not changing, their identity is remaining same throughout the spatio-temporal evolution of the interface, then we can simply solve the global continuity equation. Second important point is, this is nothing but again the global momentum equation, but in this global momentum equation, one only difference is that we have one additional term which is coming in the form of surface tension force. Okay, so if you see your continuity and momentum equation except for this particular term, these are nothing but identical to the normal Navier-Stokes equations for single phase flow. Okay, so using whatever the discretization process I have shared with you in through these CFD lectures, so there you will be finding discretization of this and these two equations, but the discretization of this term is missing, which I will discuss in the subsequent slide. And here you have to remember that when I will be writing this divergence of stress, then stress I will be writing in terms of viscosity times deformation tensor, and deformation tensor is half of del uj by del xi plus del uy by del xj. Okay. Now one important point is because we have seen that the cells which have complete reference phase present, there in continuity and momentum equation, density and viscosity should be used of the reference fluid, and the cells where we don't have reference fluid present, there it will be of the secondary phase, and the cells which are having presence of both the phases, There we will be using some weighted average quantity, volume average quantity to determine the properties. Okay, so that is what is done over here. So here you can see that rho is equal to alpha times rho 1 plus 1 minus alpha into rho 2, where alpha is your volume fraction. When value of alpha is equal to 1, it means my reference phase is present. Then this second term in both the equation will be 0, and I will be simply using the densities and viscosities of the reference phase. When alpha is 0, it means I am pointing to a cell which is completely filled with the secondary phase. There these two terms will be activating and first term in both the equations will be gone. And if any cell is having say partial value of alpha, for that particular cell, depending upon the value of alpha, we will be getting some intermediate value of density and viscosity. Okay. Now along with these, then we have to also solve one equation for advection of the volume fraction. Okay, so these are detailed set of governing equations which we need to solve when we are actually using the volume of fluid method for a particular multi-phase flow problem.
So this equal to जो second term है delta tau.
Yes.
तो delta tau के लिए dij को mu से multiply करना पड़ेगा.
Yes. Because shear stress tensor is nothing but viscosity times deformation tensor. Okay. Okay, now we know that whenever we do solve our governing equations in a computational manner, then what generally we need to do? We need to actually discretize our domain. Domain discretization means that, say if I have, this is my some large domain, this I will be dividing into larger number of small control volumes. Okay, so these will be nothing but my number of control volumes. Now one more important point is, we have learned from DNS of multi-phase flow that if we have to properly capture and evolve the interface with space and time, we have to consider our length scale of the grid structure so small such that we can accurately capture the interface profile. Okay, so because of this reason, typically the grid requirement for direct numerical simulations of multi-phase flow is more. So grid size requirement is actually more. More means lesser grid size is needed in comparison to that of a single phase flow problem. Okay, so that's why if you do everywhere the uniform meshing, in that case you will be finding difficulty that your computational cost will be high. Okay, because number of grid points will be more and computational cost will be high. So another technique you can use is, instead of going for uniform mesh, you can go for non-uniform mesh. Say I have some problem and it is almost clear to me that majority of the time in this domain interface will remain close to the center. So I can go for a non-uniform mesh where near the boundaries I will be going for coarser or larger spacing, and near this point I will be going for very fine mesh structure. Okay, so that is another approach. So in this case I can say that this is nothing but my non-uniform mesh approach, because the sizes of different cells are not same in each direction. Okay, then this problem is also this situation is also something which is actually phenomenon dependent. Okay, so I may have some phenomenon where I can create this non-uniformity in the mesh and my say interface is located in that particular finer zone. But for a generic problem, it may happen that my interface can reach to any situation depending upon the surrounding flow field. Okay, so that's why multi-phase community is many times the people who are doing direct numerical simulations of multi-phase flows, they use one special technique for mesh, that is called as adaptive mesh refinement. The meaning of adaptive mesh refinement is that the cells which are containing interface, only we will be refining these cells with smaller size grid, and away from the zone of interface we can have coarse sized grid. Okay, so at a single instant you can do this, but what will be happening? Interface will be changing with time. Okay, so it will be changing its spatial location. So when interface is changing its spatial location with time, then corresponding to that, I have to also change the refinement level of the grid so that finer meshes are traveling with the interface and coarser and away from the interface zone where earlier interface was present, there actually mesh is becoming coarse. Okay, so this type of moving mesh which is moving with the interface, that is called as actually adaptive mesh. So typically what we can do, we can instruct our mesh generating algorithm that the cells which contains gradient of the volume fraction, only we will be doing fine mesh in these cells, and away from these cells we can have coarse mesh. Okay, so gradient of the volume fraction is something which is giving me the indication that okay, in near these cells actually I am having presence of the interface. On contrary, it may happen many times that along with the interface, say you have some rotating or fluctuating components of velocity. Okay, so in a generic solver, only gradient of volume fraction is not only responsible for mesh refinement. You can use the gradient of any other field parameter, say gradient of velocity or gradient of pressure or other field variable also, to go for your adaptive mesh refinement. Okay, so depending upon your choice, in many cases it may happen that you want to also refine the zones where actually your where vorticity magnitude is changing significantly. So whatever the gradient parameter you want to use, so based on that, where gradient of that particular parameter is actually, or field variable is strong, there it will be going for finer meshes, and away from that it will be going for coarse meshes. Okay, there are certain rules which a typical numerical algorithm uses when they go for adaptive mesh refinement, because ultimately when they are refining, they cannot have a big jump from one cell to another cell. Okay, so that jump has to be smooth, because then only the fluxes of the reference faces will be balanced in the neighboring cells. Once fluxes are balanced, then only your scheme will be of conservative nature. Okay, so that's why to take care of the fluxes, some arrangement is done. So typically when you create initially the mesh, when you are using adaptive mesh refinement, then at initial time you create some coarse mesh structure. So at the moment, let me consider that the initial cell size is what I have created, these bigger boxes. These are nothing but at level 0. Is this one clear? Now, if I instruct to my code that, say I have some interface present in this cell, and I instruct to my code that keep level 0 everywhere, but where interface is present, there keep level 1. So the meaning of level 1 is that in this particular cell, for a two-dimensional cell, it will be dividing it into 4 equal parts. So once it is dividing this base mesh cell into 4 parts, so I can, upon one increase of level, so I can say that this is nothing but quad tree mesh structure. Okay, so base mesh is at the top. Upon increase of one level, that base mesh has converted into 4 cells. Upon further increase of level, then this individual cell now will be converted into 4 more. So now here, if I say that in this cell I have interface and my level is 2, then this level 1 cell is now further converted into 4 more cells. Okay, so what you can do, you can keep a track that if you do 2 to power 1, so for level 1, how many you have to do? You have to convert 1 into 4. So when you are doing level 1, so let me write here that 2 to power L into D, where L is level and D is dimension of the problem. Okay, so for a two-dimensional problem, for level 1, it will be doing 2 power 1 into 2, which is 4 cells. If you do level 2, then 2 power 2 into 2. So 2 into 2 is 4. 2 power 4 is. So now you can see from base level, when you have done level 2, it has converted your cells into 16 cells. Okay. Now similar way, if you want to extend this to 3D. So for 3D, how you can extend? 2 power level 1 into 3. So it means for a 3D, it will be converting each cell upon increase of one level into 8. So for 3D, you will be having a, if you have in 2D a square, then in 3D you will be having a cube. Okay, so once you have cube, then you will be doing partition in other directions as well. So that will be giving you 8 subdivisions. Similar way, if you do level 2, then 2 into 3, which is how many? 32. 64. So 64 cells. Okay. So this is how, like, so this type of arrangement is called as quad tree or oct tree. So if you recall yesterday, I think Pranav has presented on volume of fluid method and he has used that term quad tree or oct tree. So this is the meaning of quad tree and oct tree. Now there are certain rules. When you refine, then while you are refining, you have to take care of one thing. First thing you have to take care is, if you are refining this cell, then in diagonal arrangement, okay, in diagonal arrangement, the neighboring cell to this cannot have difference of level more than 1. Is this point clear? So you cannot have a cell where you can see this is a level 2 cell, and if I only consider the outer boundary, I don't consider this dashed line, then this will be becoming a level 0 cell. Okay, so this type of thing is not possible, and ultimately I cannot create a difference in diagonal way more than of 1 level. So it means when I will be doing this type of arrangement, then there will be smooth transition of grid from more finer zone to the coarser zone. Okay, if you have smooth transition, then you will be able to decrease the error which is happening while you are transferring fluxes across the boundary. Okay, if you increase the level jump more than 1, then when you are transferring the flux of reference phase from one cell to other cell, there will be more amount of error and there will be chances of mass loss. Okay, so that's why we will be finding that our computational scheme will not remain conservative. Okay, then this is arrangement number 2. So in arrangement number 2, exact aligned neighboring cell cannot also have level jump more than. So here you can see, so this jump, so I have to create this dashed line because I cannot have jump more than 1. Okay, so similarly, if say this is my interface, and when I am creating this quad tree mesh, so it will not be happening that in one cell I have interface with fine arrangement and in other cell I have interface in very coarse cell. Okay, so there also, if interface is shared by two neighboring cell even in a curved way, then also we have to create, and of course this point is being taken care by, particularly if we are using the gradient of particularly gradient of volume fraction. Okay, so this is about the adaptive mesh, and adaptive mesh is a need for multi-phase flow problems, because if you go for complex multi-phase flow problem where you can see that say your interface is breaking into micron sized droplet, so you cannot create in a larger domain everywhere the micron sized grid structure. Okay, so then your computational cost will be excessive. So that's why what we need to do, we can create fine meshes only in the zone where I have micron sized droplet, and away from that I can keep on decreasing the level and I can go with the coarser mesh structure. Okay. Then, so this is the C1 depiction. So here you can see when this interface was represented by this red colored line at some time t1, then this was the mesh arrangement. So you can see as you are moving away from the mesh, then one by one level is actually decreasing. And say this is the same interface has evolved with time and now it has acquired some new shape t2. So when you have moved from T1 to T2 instant, then along with the interface, your mess distribution has also actually evolved. Okay. So though adaptive mess refinement is also in certain solvers implemented for unstructured messes also, but majority of the time it is better to use this with the structured messes, because in unstructured messes, if we go with the say large level of refinement, then if you use finite element method, then there is no problem, because in case of finite element method, the node points are used on center of the control volume as well as on the boundaries. So number of node points are more than one in a single element. But in a finite volume method, where number of node point is only at the center of the control volume, there it may give some errors if your cells are too much skewed and not aligned with the interface. Okay. Now, if you have gone through the discretization of Navier-Stokes equations, then you might have heard of one first thing, you might have heard of two types of grid structures which we may have to use for the discretization of Navier-Stokes equations. One is called as collocated grid and other is called as non-collocated or staggered grid. Okay. And what is the reason? The reason is that if I have highly oscillating pressure field in any phenomenon or in any physical domain, and I am using uniform structured grid. Okay. In that case, I will be finding that the numerical discretization will be giving me highly oscillating gradients of pressure. So for one set of cell faces, it will be giving some high value positive gradient, and for other cell face, it will be giving the zero value of gradient. So if you have some highly oscillating pressure field, then in your physical phenomenon, there will be existence of the pressure gradient, but when you will be transferring it to the computational domain, on a computational domain, if you are using uniform structured arrangement, then there can be issue of pressure gradient for one cell face to be high, for other cell face to be neighboring cell face or next adjacent cell face to be zero. So that is called as actually pressure checkerboard problem. So it means you have to keep this thing in mind, that if you are using a structured grid, then majority of the times for solution of Navier-Stokes equations, we go for non-collocated or staggered grid arrangement in order to avoid the checkerboard, pressure checkerboard problem. Okay. On the other hand, if you are going for unstructured mesh, then you can use actually your collocated grid only. Now, what is the difference between collocated and non-collocated grid? So typically a collocated grid structure is one where on a single node point, you are storing the values of all field variables. All field variables means all scalars and vectors. For example, vector can be velocity vector, which will be containing u, v and w components. Scalar field can be pressure, and many times our property is also used. So say rho and mu also I can consider in the scalar field. Okay. So, and of course, if you have heat transfer involved, then temperature is also there. So if you have grid structure something like this, where you can see this blue arrow is shown with, so x component is shown with blue arrow, this vertical component is shown with red arrow, and this black dot is showing actually pressure and volume fraction, which are the scalar quantities. So if all are stored at single point, then we call our grid as nothing but collocated grid arrangement. Okay, but if I use the other arrangement, that I am storing my pressure, alpha and temperature etc. at the cell center, and I am storing my velocities at phase centers. So I am vector quantities actually I am storing at the phase center. So it means now I have two nodes. One node is for scalars and other nodes. So here this node is for velocity, and in the vertical direction this node is for vertical velocity. So this type of arrangement is called as non-collocated or staggered grid arrangement. Okay, so many times few solvers, this depends upon the type of scheme you are using. Many times this staggered arrangement is also helpful because the center of control volume you can define as your scalar node, and the face centered values you can define your vector nodes. So if you define these face centered values your vector nodes, so at these points you will be knowing the values of velocities, and it will be easy for you to calculate the fluxes of momentum across the cell boundaries, because at cell boundary itself you know the value of velocity. If you don't know velocity at cell boundary, then you have to do interpolation from the neighboring cell values to determine at the cell face. Okay, so that step is not needed once you use this type of arrangement. Okay, all are clear with this idea? Now comes the last thing which we are left with, that is discretization of the surface tension term. So we know that surface tension force F sigma delta S can be written in terms of sigma curvature N into delta S. Okay, we also know that this delta S function, which is nothing but a function which is activating only at the interface, this can be written in terms of gradient of the marker function. Okay, so this is nothing but a marker function. Okay, so now if I have to find the value of surface tension force in a discretized manner, so in a discretized manner means I need to find this value for cell I comma j for a two-dimensional grid structure. So if I have to find at cell I comma j, then I will be using sigma times k h. So h subscript over here is used to refer that wherever h is written, it means there we are using finite difference method to calculate that parameter. Is this point clear? So the places where I am not using h, that you will be finding in your discretization of Navier-Stokes equations, there we are going for finite volume method approach. Okay, but the places where I am using h, it means I am going for the finite difference method for estimation of that particular parameter. Okay, so sigma k, so k also mean curvature I need to calculate, and then this gradient I need to actually calculate, which will be identical to my delta function. Because why identical to delta function? Because this will be non-zero only for the cells which are at interface, and for all other cells it will be 0. And then I need to multiply it with normal, because surface tension will be acting in a direction normal to the interface. One important point you have to know over here, when I am writing only this much value of the surface tension force over here, I am considering the assumption that I am using completely pure system. It means there is no gradient of surface tension. Okay, I am using pure system. At the same point of time, I am making second assumption that there is no temperature gradient present across the interface, because we know that if there is temperature gradient, then also surface tension is a function of temperature. Okay, so if for some fluids the temperature range in which we are operating, if that is so small that the change in surface tension value is very small in that zone, then also I can use this particular equation. Is this one clear? So that's why this component will be acting in the normal direction. Now we know that normal we can compute from the gradient of the color function divided by magnitude of gradient with the negative sign. Okay, so this is how we can compute the normal. Now Fij, I can write that if I use this definition of normal in this equation, then I can write my Fij as minus sigma kh into gradient of color function. Up to this point, is it clear? Now let me assume a situation that I have steady flow situation, I have a static fluid element. Means my fluid element is actually not moving with time. So purely static fluid element, say a bubble or a drop I have, but it is stationary. Okay, and also it is of spherical shape. So shape at the moment I have not introduced, but at the moment simply I am considering that it is spherical. So if I have a spherical, purely spherical system, then what I can do for that, what will be happening if I have motionless system and only a spherical bubble or a spherical drop? So the shape will be balanced by hydrodynamic pressure and surface tension forces. Only these will be acting. Rest everything is all viscous terms are not there because there is no motion. There is no advection term because no motion. If it is stationary, not changing with time, so temporal term is also 0. So for that situation I can say that pressure force will be and surface tension force will be balancing and will be becoming equal to 0. Okay. So if I use this definition, then I can say that, say, gradient of pressure can be written in terms of minus sigma into curvature. Now if I am saying that I already know that shape is spherical, then I can write this as sigma k naught into gradient of color function is equal to 0.
Body force including body force.
Body force you can include, if you want you can include. So the way I have introduced the body force, in that case then what we need to do, we also need to use some reference to balance the hydrostatic pressure then. Okay, so that part at the moment I am not considering. Okay, I am considering, say, the pressure which I am using over here. This is the modified value of the pressure which is already including the body force component. Okay, so when we write modified pressure, then what we do, P minus rho GH. So that is, say, already included. So if you use this type of formulation, then you can easily discretize this equation, this gradient. So this equation can have two components now, del P by del X I cap plus del P by del Y j cap. Similarly, this gradient will be del C by del X I and del C by del Y j. So you can write component wise equation and this will be the discretized form. Okay, and from this discretized form you can simply conclude that you have this type of simplified situation. Then pressure at any cell Pij which is within the this cell Pij is within the fluid element. Okay, that will be nothing but equal to P2, where P2 is constant pressure in the surroundings. Okay, so constant pressure in the surroundings is P2 minus sigma k naught into Cij. Okay, so this is a very simplified system. So this much simplified system actually we will not be getting. So what we need to do, we need to make it little bit more generic. So to make it more generic, what I am doing now, I am writing that, say, Fij is equal to sigma times gradient of n into gradient of C. So same equation but little bit algebraically manipulated. Okay. Now to calculate the normal vector, I am using nothing but indicator function. What is indicator function? Indicator function is nothing but smoothed version of color function. Okay. So one important thing I can do now, I know that my density for interfacial cell will be equal to rho 1 into h, h is say marker function, plus rho 2 into 1 minus h, which can be written in terms of rho 2 minus this capital bracket rho s into h. What does this mean? Rho 2 minus rho 1. Okay, so this means nothing but rho 2 minus rho 1 into h. Now if I take gradient of this equation, then what will be gradient of this equation? Gradient of rho will be equal to minus rho s, which is nothing but rho 2 minus rho 1 into gradient of h, because this rho 2 is a constant quantity, so gradient of rho 2 will be 0. Okay. Now what I can do, in the previous equation now this gradient of h, or say mix of symbols is done, so let me write here h only. So gradient of h can be replaced with gradient of rho divided by rho s into gradient of H at n cap. So it means that I can also determine the surface tension force by calculating the gradient of density function and by calculating the gradient of normal vector. And what is gradient of normal vector? It is nothing but my curvature. Okay. So when I have written this definition, so this definition is identical to sigma k into gradient of C, but this k is replaced with gradient of the normal vector. Is this one clear? So now what I can do, in order to find the gradient of normal vector, first I need to calculate normal vector. So how I can calculate normal vector? For calculating normal vector, I need to calculate this slope m, which we have done previously also. Okay. So this slope first I will be calculating at corner, right top corner. Okay. And this will be coming x component, this will be coming y component, and then ultimately at the cell face, this will be mean of all the corner points. And if I have calculated like this for all the cells, values of mx and my, this I am not explaining in detail because this already I have discussed in the previous class, that how to calculate the value of m at cell center and at all the corners. Okay. So now depending upon our requirement, I can calculate the m vector using the values of color function, which we have done previously in the previous lecture. Then from that color function, now I can calculate normal vector. Normal vector will be nothing but m was the normal vector and n was the unit normal vector. So magnitude of normal vector, normal vector divided by its magnitude will be giving me the unit normal vector. Okay. So now using this formulation, I can calculate the value of n, and then if I know all magnitudes of m, then I can calculate n. But when you are calculating n, you have to take care of one thing. This magnitude of m for cells which are not containing interface, for these cells this value will be coming equal to 0. Because what is this m? Normal to the interface. The cells which are not containing interface, there ultimately the value of m has to become, so in the neighboring cells, because of the presence of color function in surrounding, it may have some value, but if you move far away from that, then value of m will be becoming 0. So if you implement this formulation in your discretization scheme, there are high chances that you may get 0 by 0 form. So this will be giving you error, because your computer will not be understanding what is this. So that's why what you can do, you can add some infinitely small floating number here. Okay, so you can add infinitely small floating number in order to avoid that error. So this is one way. Other simplest way is that you calculate this value of normal only for the cells where gradient of color function is non-zero. So where gradient of color function is not non-zero, is 0, there you don't calculate this normal, because ultimately surface tension force will be coming at the interface only. Okay, so this thing can also be done. And now we have calculated normal. We know the value of density in all the cells near the interface. So I can easily calculate gradient of density using finite difference method. Okay, so gradient of density can be easily calculated. So say if you have to calculate del rho by del x at point I comma j, so that will be nothing but rho at I plus 1 comma j minus rho at I comma j divided by delta x. So likewise you can calculate the gradient of rho, but you need to calculate now curvature. So till now you have only calculated vector n. So to calculate curvature, what you need to do now? Curvature is nothing but gradient of normal, so which will be del n by del x I cap plus del n by del y j cap. So that is what Kij is actually calculated over here from the knowledge of the normal values. Okay. Now you can calculate the value of surface tension force. So surface tension force can be obtained by clubbing all these values and joining in this way. Okay. So this is quickly I have explained you about the discretization of the surface tension force, particularly using continuous surface force method. Okay. So I think we have almost discussed all the features, almost all the features of volume of fluid method which will be required for its numerical implementation. Now quickly we can discuss that if we apply this one for say phase change problems, actually then what are the associated changes in our governing equations and in estimation of the interfacial jump conditions, because particularly the issue with phase change will be near the interface. Okay, so first point is when you will be solving the phase change heat transfer, then you have to keep a track of temperature field. Okay, so then only you will be able to simulate your boiling phenomenon. So this is transient term, this is advection term, this is diffusion term, and this is source term for heat transfer equation. And the source term for heat transfer equation, if you are considering a boiling phenomenon, then mostly this will be acting at some interfacial boundary, because interfacial volume will be converting from liquid to vapor. Okay, so we need to estimate this near the interface. So this can be calculated in a way K times del T by del N at vapor phase minus K times del T by del N in liquid phase, if N represents nothing but direction normal to the interface. So your situation will be that interface cell will be at which temperature? Saturation temperature. So the entire interface cells, you can simply explicitly specify the value of T equal to Ts at the given pressure. Okay, and in this side and this side you can compute the values of temperature from this particular equation. Okay, so using this equation on both sides of interface you can compute temperature. So once you are computing temperature, you will be able to know the temperature in the neighboring cells. Okay, now what you can do, you can draw a straight line near the interface, and this straight line is not too much, just you will be drawing, extending it say to 1 or 2 cells in each side. So once you calculate temperature, say this is one cell and this is the next cell, and at this cell center you know the value of temperature. So this temperature minus saturation temperature divided by this distance from interface to this, that will be giving you value of gradient. Okay, so this is how you can calculate the gradient, and if you know the gradient, that then mass flow rate across the interface will be Q dot divided by latent heat of vaporization at that particular given pressure condition, because that will be the rate, that will be deciding the rate at which liquid is converting into vapor. Okay, now one small issue is, I have told you earlier that near the interface, if I don't have any mass transfer, then my velocity in fluid 1 and velocity in fluid 2 will be same. So what I can do, when I am not having phase change heat transfer situation, then for the entire cell, though it is containing interface, but for the entire cell I can specify a single value of the velocity field. But when I have mass transfer, in that case what will be happening? During mass transfer, interface fluid 1 and fluid 2 velocity across the interface will not be same. There will be some different velocity in fluid 1 and different velocity in fluid 2. Then only interface is getting converted, some fraction is converting into vapor. Okay, so because of this there will be some motion near the interface for these fluids. So that's why for interfacial cell when we will be now defining the velocity, that velocity will be nothing but velocity of vapor phase time h plus velocity of liquid phase into 1 minus h. Okay, and then if you calculate the divergence of velocity for liquid and vapor phase, that is 0, but divergence of overall velocity field will be now uv minus ul into delta L, where uv and vl are actually normal velocities. So the way I told you earlier, and now this information we can utilize to calculate velocity jump. So as per, this is the amount of vapor relative to interface, and this is the amount of liquid relative to interface. This is equal to m dot. From here, if I eliminate v, then what will be happening? Value of uv minus ul will become m dot into 1 by rho v minus 1 by rho 1. So from this equation you can see that whenever your liquid is converting into vapor, then depending upon the values of density, it will be occupying different area. Okay, so that area conservation will be taken care by this particular equation. And if you calculate gradient of u near the interface, then uv minus ul in this equation you can replace with this particular quantity. What does gradient of velocity represent? Gradient of velocity represents, from basic fluid mechanics, nothing but volumetric strain rate. What is the meaning of volumetric strain rate? How much your control volume is deforming in given amount of time. Okay, deformation of the fluid element in given amount of time. So when you are estimating the deformation of control volume in given amount of time, that extension is actually dependent upon the rate at which liquid is converting into vapor, and that will be also function of their densities. Okay, because 1 kg, so can you carry 1000 kg of air in your hand? 1000 kg of air, can you carry? But you can keep 1000 kg of air in a small container. You can keep. Okay. So that is what. The point is, same mass can be kept in a small volume, or same mass can be kept in a large volume. So what will be happening, particularly when you are considering the liquid to vapor transition, then you will be having large density ratio. If you have large density ratio, for small change of mass from liquid to vapor, there will be significant increase in volume or area. Okay, and increase of volume or area is given by divergence of u, which is nothing but a volumetric strain rate for a fluid element. Okay, and this volumetric fluid rate for interfacial cells we have related with amount of mass transfer and the corresponding density values. Okay, and ultimately, if you have to calculate interface velocity is assumed to be average of the fluid velocities in each phase plus flux of velocity introduced because of the phase change process. Okay, so because of the phase change, how much flux of velocity is actually introduced. So average of these two quantities can be considered your interface velocity. Now again, I am not saying that only this is the way to solve phase change problems, because to solve phase change problem, different people have actually evolved different methods. Even to calculate this value m dot, people have actually developed some semi-empirical relations also, rather than going for this exact formulation, and there are large number of methods available where you can go with little bit more simplified set of equations to determine how much mass is converting into vapor, and accordingly you can actually calculate the volumetric flux. Okay, so this is a very brief idea that what additional things we need to consider once we have the presence of phase change. But this is not only the unique way, there can be other ways also in different solvers or different papers whenever you will be say reading for your future studies in the area of phase change heat transfer. If you study, then you will be finding there can be different ways to implement the numerical solver. So this is these are some results using this particular methodology when film boiling is done in a surface. So this surface is subjected to some constant heat, so this surface is given some constant surface temperature which is higher in comparison to saturation temperature, and this is very high, so the boiling is actually getting converted into the film boiling regime. So here you can see this entire surface is covered with a layer of vapor, and the zone where vapor is actually growing in size, then because of buoyancy it is rising and it is pinching off some bubbles. And using this method, if you calculate, this is the surface average Nusselt number and this is the time average Nusselt number. So if you plot time average Nusselt number as function of Jacob number, then this numerical model is matching mostly with this modified Bernanson equation, which is an empirical equation for determining the heat flux in case of film boiling regime. Okay, and this is some representation of phase change heat transfer, particularly in the nucleate boiling zone. So what is the meaning of nucleate boiling zone? In the previous case, you have seen that the entire surface was actually covered with a film of vapor, but in this case only the vapor bubbles are forming from some specified locations. So these are nothing but called as your nucleation sites. Okay, and from these nucleation sites you can see that your vapor volume is growing. Once its size is becoming sufficiently large, then it is leaving the surface and again it is new vapor volume is actually starting evolving from the residue. Whenever you study the problems of nucleate boiling, then one very important phenomenon come into picture, which is called as actually micro layer evaporation. Okay, so typically what happens from a nucleation site, say this is my surface, this is the nucleation site from where vapor is forming. So this vapor, while it is forming, it will be creating volume something like this, and beneath this vapor you will be finding a very thin liquid film of micrometer size. Okay, and in this liquid film what will be happening, because liquid film has high thermal conductivity, so it will also carry certain amount of heat, and because of that this heat will be actually reaching to this interface. So along with the amount of vaporization which is happening from this site, there will be some amount of vapor formation from this thinning of the micro layer. Okay, so whenever this simulation is shown over here, in this simulation actually the modeling of micro layer is not implemented. Okay, so maybe these are some complex situations where people still are developing certain methods and improving the accuracy of the methods for doing phase change heat transfer problems. So this is a continuous process. Even in volume of fluid method also, various new advanced schemes are being developed in order to improve the accuracy of interface advection, interface reconstruction, and then decrease the overall computational time of the simulations. Okay, so if you see current literature, you will be finding large number of research papers in these areas where people have written the research papers just to show new advanced methods, and then they have with their new implementations actually they have validated some benchmark problems. Okay, so with this we will close for today, but before that what I will suggest you that we have now come to know about some idea of computations of multi-phase flows. Okay, of course from the level of complexity, whatever 1 or 2 dimensional problems, very limited number of schemes we have seen, but from this only you might have come to know that what is the level of complexity. Okay, and moreover only the people who are dealing with development of methods, they need to know all these methods with each and every minute detail, because they need to implement these. Okay, there are many people who are only using the computational methods as tool to solve their physical problems. Okay, so the people who have interest in understanding the physical phenomenon and they just want to use these computational methods as tool for solving the multi-phase flow problems, what they can do actually, we can then use some standard or available tools in the market. So available tools are available in the form of commercial as well as the open source tools. Okay, so two very famous say commercial and open source tools are ANSYS Fluent, or ANSYS Fluent is commercial and OpenForm is one of the open source solver. So if you want to get some hand-on practice of these solvers, so what you can do in my one of the earlier recorded course, I have some recorded lectures on hands-on practice of ANSYS Fluent as well as the open form. So I have given the links of these lectures and you can go through that. So first lecture is for Introduction to ANSYS Fluent Interface. So how graphical user interface of the ANSYS Fluent looks, and then what are the different steps you need to do to run a simulation in ANSYS Fluent. So you can go through this tutorial of plain Poiseuille flow problem. And then, so how to set different boundary conditions and how to define the models. So all that information actually you can do, and if you follow this, I think you can repeat the problems what are shown over there. Then second is, this is a single phase flow problem, but if you want to use ANSYS Fluent for a multi-phase flow problem, so simulation of dam break problem is also shown using the ANSYS Fluent. And then one lecture is on Introduction to Open Form Interface, and then simulation of dam break problem using the open form. Okay, so these are only 3 lectures. I think if you go through these lectures and you start just following the instructions, then you will be able to get some hands-on idea of the computational tools. Okay, so with this we will be closing this course ME 514 Fundamentals of Multi